Okay, thank you very much. Yeah. So I'll just remind where we are. Let's start in infinity station. We have compact manifold with T-moles compact structure, symplectic structures, you want up to deformation and torsion B field. Then, if I count Gromov-Witten G0 Gromov-Witten invariants, I get some quantum product on super vector space. So it will be really treated as Z2 graded space, not Z graded, which will become homology of my manifold with coefficients in the field, which I reminded was rational number typically, or cyclotomic field if I do some torsion. Okay, so I get this product, and the product, it will be not one product, but depending on many parameters. Number of parameters is the dimension of cohomology of the rational coefficient of my space, and parameters are of two types. Will be variable t, which could be even or odd, corresponding to even or odd part of homology, and q, which correspond to some to h2. And variable q could be, in fact, I don't have to go to the full second homology group. It could be some smaller number of parameters q, because when I make genetic series, I put attribution of each homology class beta as a q monomial product of qi to some power of some integrals. And I want to be because it will be form power series, I want these integrals to be integer and positive. Two integers guarantees that homology class are image of second homology with integer coefficients in real second homology. And so the first constraint that things are non-negative and get non-negative integers. But now when I make the whole series, I want for each coefficient to have only finitely many betas to contribute. Now for this, and when you calculate correlator, you know what is the dimension of moduli space, because it's the dimension of fields you should put in. So what it results that if you're interested how many homology classes of curves which are G-effective, represented by G-holomorphic curves, and with given integrals of my forms omega and also first Chern class, then should get finite number. And this integrals lies on not on an octant, but on octant times integers, because integral first Chern class would be arbitrary. Okay, so if I have this finiteness, then I have a well-defined genetic series. So in my original story, in this infinity case, I said that number of parameters q was equal to the rank of second homology. I take some basis of second homology. In the algebraic case, I take smaller number, rank of neuron severity group. And in general, if we have Keller manifold, it didn't have H20, then algebraic curves lies in H11, so they really have smaller rank lattice, so you don't need to go to measure degrees with other classes. So we can make smaller numbers. And in fact, one can go even to number one of parameters q. Just pick one ample line bundle, and that will be guaranteed finiteness. And when you do decrease number of variables q and trade them for variables t, there will be no loss of information. You get series which satisfy some properties that they come from series is actual right number of q. Yeah, so it's some simple remarks that one can write genetic series in different number of parameters, and at the end of my talk you will see that it will be really very useful. Okay. And those whole things one can encode in some abstract notion, which is called formal log Frobenius manifold, over field of characteristic 0, which will be this rational number, so field. So let's see this definition. So we have a super vector space, Z2 graded space, okay. We have element 1, it's in examples generator 1 of H0 of your manifold. Even element, then you get non-degenerate coherent kind of fundamental class, fundamental class of diagonal. It's element of symmetric squares, which even, in fact, this word not degenerate. So the whole story one can relax. One can forget not degenerate. The whole story will work in the degenerate case, and it can be useful for a case when consider not compact manifold but something with semi-positive boundary. You still get you don't have correlators, but still get a quantum product, and the whole story works in the same way. Okay, so that's a super vector space. Now, next things which you have a formal smooth super scheme with devices normal crossing. It will be Frobenius manifold. This scheme is just equal to kind of form power series in several variables, which are even and odd, and some variables like u, L of them, could be one or many, and some even variables, and odd variables, of course, participates as exterior algebra, so it can distinguish polynomials and form power series and odd variables. So you get this abstract algebra, which is amorphic to this guy. Divisor given by equations that one of variables q is equal to 0, so it's normal crossing divisor. Okay, but coordinates are not part of the game. No, coordinates it's really not part of the game. I'll explain what is going on. So you have now we have a trivial bundle on this fiber H on product. Oh, sorry, it's not tensor product. It's product of my formal schemes and a fine line in coordinate U. So it will be formal in Qt variables and actual in variety in U variables. And then I would like to have meromorphic connection here, which has a very special form. In remind you, this connection in du du it will be have terms u minus 2 and minus 1. In du dt or q dq to have u minus 1 term, and that's it, and that should be flat. Yeah, so this, there are three matrices here. G, which is constant matrix, it's just a constant even operator, but K and A are operators depending on parameters, on Q and T. And this parameters, bunch of matrices AI, I can organize in a one form. I take some way I, dti or d log ui, get just one form with values and endomorphisms.
Sorry, what do you mean by O of F?
It's algebra functions. It's this algebra,
Okay.
which is written here. Okay, so the axiom that this connection is flat, and then there is something which allows to introduce flat coordinates on the base. Namely, you apply this matrix value to one form, to this vector 1h. And we get one form with values in super vector space with logarithmic poles. And this axiom that this thing gives an isomorphism of logarithmic tangent space and trivial bundle. When you get these things, you pick any coordinate in h, you get one form, a logarithmic form on Frobenius manifold. It will be closed form. It will be differential some function. It will be so. That's how you fix flat coordinates in this situation. And final thing, which is today played really no role, will play a role in next lecture. There is interaction with sync with the pairing. So all these operators K, A, and G, K and A are self-adjoint with respect to pairing, and G is anti-self-adjoint. And geometric meaning is this: when you have this connection, you have a pairing at fiber point u and minus u, which is symmetric under permutation. Okay. Yeah, so that's way to encode all this data in kind of geometric terms. You get manifold, bundle, connection, and all this stuff. Okay. Now let's pick a point of my Frobenius manifold over some non-Archimedean field. You can, for example, just substitute instead of variable Qt, say they're equal to certain series in some variable in capital T, some new dummy variable, which starts in positive powers of T. And powers could be integer, rational, real, as you like. And then the whole thing will make sense. I get convergent because coefficients were rational numbers and have evaluation 0. If my series are convergent for some embedding of field in complex numbers, then I can make actual complex numbers instead of things. And now, for a moment, I want to forget about most part of the whole story, this unit element, copairing, connection along Frobenius manifold. Just I have operator G, one even operator, and another even operator K at a given point. So I get vectors, super vector space, maybe of some larger field, and two even endomorphisms. And super will play absolutely no role. One can forget about the super, just take direct sum of two vectors, even on part. Yeah, so that's the basic object of linear algebra for a moment. Will be vector space, so super can forget, and two endomorphisms, and then it gives you a connection and trivial bundle. Now, so that's the central object in all the story, this connection of this special form. So now we want to understand what does it mean to have such a connection. We can approach it in the following way. So first of all, if we remove 0 from a affine line, then I get a vector bundle, trivial vector bundle with a connection, algebraic connection, with the same bundle. And section of the bundle is Laurent polynomials in U with values in my vector space. Now I want to say that this bundle is trivialized. So what does it mean? I can extend it to 0. Let's set the formal neighborhood of 0, and in this case, just take Laurent Taylor series in U. And when I extend to 0, I want to ask that the connection have pole of order 2. Yeah, so before I have just abstract algebraic connection, but now extended to 0, so the pole has an order 2. Also, I can extend it to infinity. Just take again Laurent Taylor series in U inverse.
Not me.
Yeah, and this guy, if one can easily check, has a pole of order 1 at infinity. So if you get U du, it will have no poles at infinity. Okay, so and then we get glued bundle, and this bundle is trivial, just by and conversely, if you have your algebraic bundle on I1 minus 0 and extend both to 0 infinity such that the global bundle is trivial, then the same is you get just vector space of sections, and then automatically you'll have this expansion, because in the trivialization you write what is your connection. It will be certain Laurent polynomial in U, and the conditions has second order pole of 0 and first order pole at infinity. Says that the Laurent polynomial has only two terms, k minus 2, k minus 1, which denote k in G. Yeah. So that's just kind of geometric reformulation of this formula that we get some bundle.
Then this is just like the elementary stuff, right?
Everything is elementary.
But this in particular.
This is particularly elementary, yeah. Yeah. So. Yeah.
Why do you call it a manifold when it's clearly linear?
Sir?
You call it a Frobenius manifold when it's linear?
It's linear, yeah, but later you'll see some. Yeah, it's kind of it's historical notion. You get Frobenius manifold, but it has some kind of metric function, blah blah blah. Yeah, of course it's linear space. Yeah. Yeah, quantum product. You get multiplication tangent bundle depending on a point. You get a fine structure, but also get. Yeah, so it's tricky business. So now. It will be convenient to develop some intuition what to do with these equations to make a Fourier transform in inverse variable, U inverse. It will be still kind of considered like coordinate of some another affine line. And we get harmonic demodel some dual coordinate, Z. If you look on kind of dimension, Z will be proportional to U. So it looks to be no reason to make any notation, but it's really a different letter. So my D module, which I have before on a line, punctured line, it's a vector space is the same, Laurent polynomials in H, but the structure of D module in coordinate Z is given because we apply what is Fourier transform and exchange derivative and multiplication, and then we get the following formula. So consider this vector space, all Laurent polynomials as values in H, and define operator Z as u squared u plus k plus ug. So there's no poles here in u. Division disappears. And operation du dz became u inverse. So the commutator of this guy is equal to 1. It should be in valid algebra. Okay. Now, what I can do? Before I have this reformulation of my vector space and pair of operators as demodel on vector bundles connection on affine line minus 0, h and delta, nabla, and then I get extension to 0 and extension to infinity. Let's forget about extension to infinity. So it will be a slightly different structure, Wiki structure. And how to formulate the whole story in terms of this guy E. So we can formulate this the following way. We get, so we say that we have d module in variable z. The fact that the whole story has some kind of regular singularity in infinity says that this model has regular singularity to infinity, and the rank homology of this affine line coefficient with this d model is 0. So what does it mean? Maybe I just explain. If you have some d module E, how to calculate the rank homology? You multiply E to 1 forms of affine line multiplied by functions of affine line to E. Yeah? Gamma of E. We get this Derived differential. But as a vector space, because we identify dz uses a basis, it's just the same as gamma of E du dz gamma of E. It cannot be multiplied by dz. So it's operator differentiation, and the fact that it has 0 homology, it means it has no kernel, no co-kernel, so it means it's isomorphism, so it means it's du dz is invertible. Yeah, so it's a very elementary basic fact. So this fact that my story lies variable u was invertible in the module goes that the du dz is invertible, so we get this exact reformulation of h and nabla with these conditions. But we have extension to 0 h plus. I ignore at the moment h minus. Extension to 0 is given by just this subspace. And this subspace also one can modify.
Which subspace I can see? Which subspace?
E greater than 0, maybe. Yeah. One can introduce not one subspace, but whole kind of scale of subspaces depending on integer parameter nu. You consider things multiplied by nu. One can go from one to another by this invertible operator du dz, which is u inverse. So there's really no the same information here. So consider one of the subspaces like greater than or equal to 0. And this will be submodule, because you immediately see that it's preserved by operator z, because it's only increased powers of u, and preserved by du dz inverse. So it's kind of bizarre property phrased in the way when du dz is invertible. And because it's preserved by operator multiplication by z, it's a quasi-coherent sheaf. In fact, it will be a coherent sheaf. It will be O submodule of my d module, which is it faces bizarre property preserved by du dz inverse. So we can choose any of them, but when we choose nu large enough, that it's easy to see it will be torsion-free sheaf. It will be a vector bundle which coincides with my d module outside of singularities. And what's going on? Because the service is kind of trivialized. You will have meromorphic connection on this E greater than mu. It will be bundled with some meromorphic connection, and a trivial one. And the meromorphic connection will have this form: du dz plus this g plus nu divided by z minus k inverse. So this connection depends on this parameter nu. But if you change nu to nu plus 1, it will be gauge equivalent if nu is sufficiently large, and sufficiently large it means that its negative numbers do not intersect spectrum of z. In real life example, for quantum homology, go to dimension over 2. Yeah, so it's kind of way to go from kind of a bit more abstract story about the model to something very concrete story with connections. Yeah, so now this will be why I introduce this Fourier transform, because in this Fourier transform there's something which is kind of very easy to understand, called analytic decomposition theory. Yeah. Suppose on a complex plane, which is my z-plane, I choose a collection of disks, disjoint disks, dj, and choose some collection of Gabrielov paths which goes to minus infinity, disjoint paths. So I fix this data. Now I consider two sets or categories, one can say. I consider holonomic d-modules on a affine line, which is regular at infinity. The rank homology is 0. Singular subset, singularity of the thing, it's some collection of points inside this union of disks.
What do you mean singularities?
Where it's not a vector bundle.
Ah.
The models, holonomic d-modules can vector bundles up finitely many points. And this choice of coherent submodule, which is as a subset closed under duodecim inverse, which makes sense because the rank homology is 0, and the quotient will be torsion, actually will be infinite type torsion sheaf supported at my singularities. This E plus is coherent and quotient is quasi-coherent, kind of infinite negative Lorentz terms of Lorentz series torsion. Yeah, so get this data which we came up, we're getting some stuff, and the claim that the same data it's expressed through itself in a sense. I claim that if you have such a thing, you have a collection of D modules and this subset EG plus for each disk, which will be kind of local contribution of things. This D modules will be bundles of a smaller rank, and then will be a gluing data. A gluing data, so this my Gabrielov path will play a role to kind of fix ambiguity in this gluing data. If I fix this path, this gluing data is just collection of linear maps from this point when this green paths touch the disk of one guy to fiber to another thing for any two different ordered pair of disks. Yeah, that's arbitrary maps. Yeah, that's maybe I explain a little bit the story about around these maps. Yeah, this construction is purely transcendental. It's not algebraic construction. It's kind of Riemann. It's based on its Riemann-Hilbert correspondence. First, let's consider the module, which is regular holonomic D module. On a fine line with the rank homology 0. So it's, my D modules could be irregular at singular points. I don't assume it, so there's one conjecture that it's regular, but here it's a very general story. So suppose I consider irregular holonomic D module with H dram equal to 0. Because it's regular holonomic D module, it's the same as perverse sheaf by Riemann-Hilbert correspondence with sheaf. I don't know the sheaf. Sigma with R gamma equal to 0. But now it's a question of topology. What is perverse sheaf and R gamma equal to 0? So this is something which with Ludmila and Tony we analyzed 10 years ago. It's very simple. First, in this case, it's actually a constructible sheaf with R gamma equal to 0. And then one can describe in terms of linear algebra It's just a collection of some points in C, finite set. And then if you choose this path, to these points, you choose this path, it will be the same as collection of vector spaces. Then you get operator Ti from vector space to itself, which is automorphism. And then you get operator Tij from Vij for I non equal to j, arbitrary. And how these things appears this in real life? What does it mean, this constructible sheaf is gamma equal to 0? There are many ways. You can imagine, for example, that you have some map from some variety to C. This is a fine line. Just to get a map for anything to C, and which is have kind of finitely many bad points in the image. Then you can immediately get a sheaf. Namely, I'll tell you what is the stock of the sheaf at any point. The stock of the sheaf of any point, point Z, will be cohomology. You choose any index, pick I, and you choose any index of what? Of Y and pi inverse of pair. I consider cohomology of pair. And then you get constructible sheaf whose R-gamma is equal to 0. I can use actually not only cohomology, anything, like case theory, and to choose individual things. It's not really in direct category. Individual cohomology proof gives you this remarkable sheaves with R-gamma equal to 0. And now, what is, for example, the space Vi? You consider the following thing. You consider disks around the I, and the I will be cohomology of pair. Oh, sorry, maybe it's something. Cohomology of pair, and namely pre-image of the disk and pre-image of this boundary point on the disk. Here's cohomology of pair, and then one can go for arbitrary disk which contains several Zi, and if you play this game, you see you get this data, and conversely, with this data you get this sheaves. Pi? No, if you have projection. Yeah. Sorry, my potential. Yeah, it could be arbitrary map from any space to C. It's really elementary two-dimensional.
I thought they didn't have any pi in this description. So.
No. It's example. In this example, I get constructible sheaf with R-gamma equal to 0, and all the things have this clear interpretation.
I'm sorry, I'm just confused. Why is the R-gamma equal to 0? For like, if I look at the middle dimension, don't I see the vanishing sign?
It's not vanishing. It's any dimension. It's not middle dimension.
But if I pick specifically the middle dimension, wouldn't I see the?
It could be some vanishing. Yeah, it could be some vanishing cycle. Yeah.
Wouldn't that,
global.
Wouldn't that be global cohomology not equal to 0? I mean, I think.
I don't know. No, I take cohomology of. No, Vi is cohomology of pairs, and if you have really kind of like proper map, it will be a global section of vanishing cycle of this fiber.
All I'm trying to say is that
What?
the symbols of a fibration seem to define a class in Hn of the total space relative to fiber and infinity.
Yes, yeah. One can try to think.
But they don't give global sections as you move Z everywhere.
No, but what is the definition of global? I mean,
What
is R-gamma? R-gamma should.
R-gamma.
R-gamma starts with global sections.
No, R-gamma means it's zero homology and first cohomology for constructible sheaf. Yeah, it's something. Yeah. No, I consider constructible sheaves such as this has no global sections and no first cohomology. It's certain constraint and no second second cohomology will be no here.
So it's monodromy invariant ones or something.
Yeah.
Okay.
Yeah. So it's everything reduced to this stupid linear algebra, and the description depends on the choice of path, and braid group acts by automorphism of this algebra.
So then why
restricted linear algebra by modules here.
Sure? No, I explain some particular case, it's not here. I explain what is a regular holonomic D-module, get this data. Yeah. Now, what goes on here? How we get, what I claim, this gluing data, and this gluing data is exactly the same like this regular things. Yeah. How we get reverse shift of the spaces Vi from your maybe irregular D-module. So the question, how we get in my general solution, my thing is not necessarily regular at marked points. You define spaces associated to the disks. One can for each disk I define certain space, Vj, and Vj defined as the following. It's defined as the rank homology of analytic D-module of the disk Dj with coefficients in this relative to the pair point on the boundary, then my green things called, with coefficients in analytic D-module what is D-module E restricted to the disk. So it's not algebraic calculation here. I just make analytic D-module, but still I get vector spaces. And by the same game, I get this bunch of gluing data, these operators. Tii will be monodromy if you move this boundary points. And Tij will be the things. And so we get this gluing data. And then it's a bit long story how you extract this residual D-modules. You make quotient of the things. So this whole thing can be made an actual holonomic D-module in a disk. It's the same story. And then you mode out by maximal trivial sub-D-module, you get this local Ej, and Ej plus is inherited here. So you get the story that you get really one-to-one correspondence. You glue things which localized in different pieces by this gluing data. This also can be rephrased in terms of Stokes parameters, but it's a equivalent story that Fourier transform correspond to another. So we have this way, if we kind of bound that my moving point sits inside certain domains, then I have description as kind of individual local pieces and some this topological data. Now, if I analyze isonomodal deformation of these pairs, when I have a bundle with connection in some parameter spaces, not necessarily Frobenius manifold, then I get asymmetric deformations of, one can analyze what's going on. I have just collection of isometric deformation of individual local pieces, but the gluing data is kept constant in the story. It's kind of the Stokes deformation. And what is the corollary? If you consider analytic Frobenius manifold, which gives you some isometric deformation of such guys, actual of complex numbers. So if you analytical Frobenius, but should go outside of divisor because my connection is kind of single root divisor, then the whole thing splits as a modulus as a product of certain kind of weaker things as Frobenius manifold, like deformation of pieces in individual disks. And so these individual guys will be not exactly Frobenius manifold. They carry flat connection on a bundle, regular to infinity, second order pole, but there's no this trivialization at infinity. There's some little piece of data is missing. And in order to get Frobenius manifold, one can extend this guy to infinity, this bundle on a fine line in U variable. And because we extend using the extension to have poles of order 1, it's the same as to near infinity. We choose a locally constant filtration, like by integers or say near infinity, and then the defined kind of extension canonically. It's the same correspond to extension of your bundle to this connection first order pole. It's some kind of framing. In a real life situation, there will be some lattices, and this filtration will be an integral flex, so there will be no continuous parameters here. So it's essentially said that this Frobenius manifolds, if you organize these things in several disks, splits in the product of other Frobenius manifolds with different affine structure. That's the main story here. Yeah, so it was analytic version, and it took us in really too long time because we wanted to translate it to something calculable without transcendental methods. And it took us really long, many months, and eventually we got translation to really formal version, which turns out to be very easy. So one can forget about all this complicated gluing data and so on, and it will be formal log version. So we start with again field of characteristic 0. We get a formal introduce some kind of notion which will be convenient here, formal log U connection. What it will be? You get a formal supermanifold with only one base point, so it will be spectrum of formal power series rings in even and odd variables, and there are some. This device with normal crossing, so some even variables called Q. T could be even and odd. Then I get a super vector bundle on these things, and now variable U will be formal variable. And I want to have flat member of connection with the same pole constraints as I had before. So when I consider covariant derivatives with U squared du, U dti or UQi dqi, I get something which has no poles defined operator from sections to sections. Yeah, so I get this abstract guy. So I don't assume that the dimension of the base is equal to the rank of the fiber. It could be just any family. But in this situation, I have an operator acting in the fiber at 0. Namely, I take this covariant derivative of U squared du, and it gives you operator at fiber. It's well-defined term, so you get certain endomorphism of this vector space. Now, this is a very simple analog of this my decomposition story for in this formal world. Now, assume that my supervector space with endomorphism sitting at point 0 is decomposed as direct sum of certain subspaces with endomorphisms, and different pieces have no common eigenvalues. It will be things like disjoint disks containing different eigenvalues. I put some eigenvalues here, some eigenvalues there, so it will be like collection of disks, but in a completely formal way, so it works on any field. And the claim in this case, this decomposition at point 0, you can extend uniquely to the whole neighborhood, formal neighborhood, and this U and Q variables, everything is form power series, such it will be direct sum of these formal log U connections over the same base. And proof is very elementary. It's just step by step in U expansion. You see that you should divide by difference of eigenvalues. You get some.
Should I imagine that this is the case because somehow you're taking straight arcs going to the left instead of taking an arc?
No. The main idea is that if you go to formal classification of differential equations, you forget about Stokes data, you forget about gluing data. Yeah, okay. Yeah, that's the intuition here. Yeah, so there's no gluing data here. It's much simpler here, and so you get this. There are two results. It's the first one that you have formal decomposition theorem. Very elementary, just step by step. And there is another one. I recall that for go from this stuff to actual Frobenius manifold flat coordinates, we need to choose some framing. What will be framing if you work in form power series without assuming any convergence?
Sorry, the framing from the other point of view was what was happening at infinity.
Yes.
Now you're phrasing it in this thing even though it's formal here.
Yes. Yeah, framing is the following. Suppose I have a formal log U connection. It's still not flat coordinates, it's like extension to infinity. It's a choice of trivialization called phi of my formal bundle. So I just identify this base multiplied by constant vector space, supervector space. And such that my connection have exactly these right terms. 1 over square, 1 U. So you can now extend to U sitting in projective line. Okay, you get these guys. In fact, one can prove from the equations that G is not a function, it's a constant. And there's a second theorem, which is a little bit more difficult, but not much. It's extensional framing. Assume that we are given a trivialization of my bundle, which is given the framing if you go put your parameter q and t equal to 0. So it will be in just a variable u, we make it straight, and also derivative of qi due to qi also make it straight. These things do not change if you make change of framing trivial at qt equal to 0. This exactly these three terms, this ai terms will stay the same. They don't change. Yeah. So now this k tilde, k minus 2 tilde, k minus 1 tilde, and this a minus 1 I corresponding to q variables are not functions, just operators, even an endomorphism of H. Now the assumption is, suppose that these guys are all nilpotent, ai are nilpotent. I don't really understand intrinsically why it's so, but it's calculation shows that's the right condition. Actually, not necessarily that condition could be nilpotent plus constant. Adjoint operator should be nilpotent. Yeah, suppose this all operators are nilpotent, then there exists unique framing which extends your framing at point qt equal to 0. And the proof is step by step, again, in qt expansion. If you go to variable t, it will be, you don't use this nilpotence condition, it's very easy. And if you go to q, you get some kind of tower of equations, and you resolve exactly because you're using this part as nilpotent. So it's some short calculation, which I will not show it to you. Yeah, so it's, I think it's true theorem. Yeah. Now I will tell you about applications of all this thing. It will be to, now going back to geometry. Suppose I have my almost complex manifold with tame almost complex structure, and I take a closed almost complex submanifold of codimension at least 2, complex dimension 2. Then I can make a blow up. The blow up, like in integral case, the blow up contains exceptional divisor. So outside of y do not nice, you can over y you have a fibration exceptional divisor. The fiber will be kind of normal direction from projective, complex projective space, and automatically all these guys are tame. Actually, it's kind of interesting.
I don't even know how to write down complex structure of this.
Yeah,
it's
yeah, maybe a bit. I think it's fine. You still get almost. Maybe we can deform almost complex structure. You don't need really complex structure. You need up to some deformation.
I think if the complex structure is integrable near the point, I can do it.
Yeah.
It's not
It wouldn't
Yeah,
be
no.
differentiable.
Sorry?
It wouldn't be differentiable in general. It's linear, so it doesn't work.
No.
But anyway, you can make it integrable near.
Yes, yes. And I claim that I can also make check that the same. That's actually not totally trivial story because on x tilde you have some symplectic form on x. You take pullback. It will be not positive. It will be semi-positive. But then you get like a canonical class. And then you can make linear combinations, and canonical class make its positive along divisor. And then you can make appropriate linear combination, take pullback of Keller form with very big multiple, so it will dominate outside of divisor, and near divisor you get those things will have positive. Yeah, so the same story actually true in algebraic geometry. If you have projective variety, you get smooth subvariety, it will be automatically projective, it's trivial. But if you make blow up, it's also get projective by kind of similar reasoning. Okay, as I explained to you in the very beginning, when you write this Frobenius manifold, to write coordinates q, we are kind of free to do whatever we want. We can make smaller number of q, larger number of q, and I'll take only one q. And for this I use only one symplectic form on x with integer homology class. And use as a form controlling my stuff upstairs and the blow up the pullback of this form x. It's not strictly positive. But in all this business, when I want to make form over series, we should have finiteness of homology classes if we fix degree with Pigma form and degree with first Chern class. And both together make again your ample class, so you get finiteness on the nose. So one can go to this semi-positive guy cell in this case. And the goal of all the story is to calculate, use this point around which we make all expansion, and calculate Gromov invariance of x tilde in terms of Gromov-Witten invariance of x, y, Chern classes of normal bundle to y, and the restriction map comparing homology and comparing varieties in this case. Yeah, so it will be certain universal formula, so which all this procedure will give. So we have this base point when variable q equal to 0, t equal to 0. So curves, when q is equal to 0, it means that I have curves which have degree 0 with respect to this degenerate form. And it means that if I project down to x, I get a point. And there are, so it means that there are things of two types. Either get constant map to x tilde, which was from the very beginning, or I get non-constant map, but they should lie in one of these projective spaces in vibrational exceptional divisor. Now consider quantum multiplication at this limiting point by this first Chern class. And by dimensional reasons, because I see that among this non-composite curve in projective space, only lines in the curves of degree 2, 3 will give too large dimension. So I get just two types of thing. And if I identify this canonical identification of cohomology of SZ2 graded space, cohomology of x tilde and cohomology of x and many cohomology of y, when I get this operator, I get something like this. It's here the piece corresponding to homology of x. And here multiplied by first Chern class of x. There will be nilpotent operator. Then there will be something mixing this together, some operator class. And here I get such matrix. This comes from a multiplication of first Chern class of this dx, which will be this projective space. And it will, it's constant maps. And this guy comes from multiplication coming from lines. It's a kind of basic calculation. Solid calculation you know how to do on all this Gromov-Witten invariance, like calculation of projective space. So I get this matrix. And then you immediately see that the spectrum, it's very simple. It gets 0 because many times from this guy. And you get m-1 times m-roots of 1 from this operator. It's something like contribution of projective space.
We're assuming that.
But each of them has multiplicity cohomology of y.
Yes, it has multiplicity of cohomology of y, and this has multiplicity of cohomology of x.
We're assuming that x is Claviat, or?
No, I don't assume anything.
But it's a classical product.
It's a classical case, and
Okay.
yeah, this canonical bundle will be essentially.
But shouldn't we see the quantum products?
Maybe I'm wrong. It's m-1 plus, sorry, plus classical multiplication, which is upper diagonal. Yeah, so it's a little bit more complicated. Maybe you're right. It's something like
no,
you get
quantum q equals
you get m-1 over diagonal, and then you get quantum. You get classical. Sorry, yeah, yeah.
Q is long.
I think we're having a debate about whether this is the classical product with C1 of Tx or the quantum.
What does Q equals 0 mean? Q is like log T.
Yeah? Q equals 0, yeah, okay.
So Q equals 0 means like?
Classical product. You raise Q to power degree.
It's a classical product because it's Q to the beta. The degree 2 part is Q to the...
Q to the beta, yeah. You consider just constant term. Yeah, so it was a little mistake here. It's not m-1, but each block it's kind of constant matrix plus nilpotent matrix, but it still doesn't change anything with the spectrum. Yeah, so get a bit complicated guy. Oh, by the way, one also have grading here, and the claim when you write this equation, make Fourier transform, you get Mativik variation of hot structure, which is not obvious, but it's a true fact. One can write monodromy, explicit matrices.
So what is the change was again?
No, the changes here. It's not a constant because it's actually a block. It's homology of y. It will be multiplication by constant plus classical multiplication by first chain class of dy. Yeah, so it's a bit. Should add m-1 plus multiplication by c1. Okay, so one gets this.
So can I also, what does the upper right corner mean?
It's again minus. It's just minus one.
Which vector spaces does that go?
It's homology of y to y because this is y. It's also y here.
So in that decomposition, we're not seeing the x part.
No. I think it's kind of a block upper triangle here. You got this spectrum and this spectrum, and this is apparently in some on the second part. So spectrum are really union. And connections of yeah, so it's pretty complicated connection, but it's the claim if you make this Fourier transform, make this division, this blah blah blah, it's actually some homology of some mix variation of some mixed structures, kind of homology geometry, which I didn't figure out. Okay, yeah, so that's the calculation. And what really goes on? So consider spectrum at the limit point. You have 0 and roots of 1 multiplied by constant. So it's an x of y with homology of x, homology of y. Many times. Now that's a limiting point. Now we deform variable to Q and T. I claim what happens. This point will separate. You get more eigenvalues, exactly like rank of whatever you should get here, and one can do a simple calculation. Let's consider projective subspace and a projective space. It's a toric variety. We know everything about Fano toric varieties, and this is given by Laurent polynomials, and Laurent polynomials is this guy. And if you ask your computer algebra program, or you can do it by hand, calculate critical values, you get exactly this picture. You get small things which looks like almost regular polygons of right size, and which will be contribution of projective space. It's regular polygon without 0. So you get these things without 0. And now we can apply formal decomposition theorem, because my Frobenius manifold will be locally have my variation of things will be product of different variations. For each variation, I have used extension of framing theorem. So I get a new framed connection of my Frobenius manifold, and it's kind of locally outside of the divisor will split in a product of small Frobenius manifold with new things to get a fine structure. So you get some one forms. You get a lot of closed apparently one forms. Now apply elements. One in IHX and one in IHI in this identification. Then I get vector space value at one forms and gives you flat coordinates. So you get new flat coordinates for individual factor, and it will be some kind of individual Frobenius manifolds. And the conjecture the small Frobenius manifolds should be Frobenius manifolds of x and y. Who else this should be? It has the right dimension. It's completely universal. Yeah. I don't have a proof, but it looks natural for many reasons, and like you get like Foucault categories, pieces of Foucault categories have the same size, the same dimension of model as Foucault categories. For why should be different one? They already have a universal family. Yeah, so it's not real proof, but I think it's maybe proven already. We'll hear on Thursday talk by Lee. Yeah, so maybe it's already zero. So it's at least it's very well formulated conjecture, and something which completely kind of algorithmic. One can put make from it closed formula. Computer can calculate it, and it can actually solve algorithms. It can make formulation arbitrary operands instead of things we can make about algebraic cycles. All these things like Cho operand. Yeah, so it's completely general conjecture which should be proven in two worlds, both in symplectic world and in algebraic world. This should be yeah, so that's maybe the end of the story. So.
Questions?
So, when we do these formal splitting, usually when we do a sort of coherent about certain decomposition in higher dimensions,
What you say? I didn't listen to it.
when we did the splitting of the formal differential equation,
Yes, yes, yeah.
so normally when we do the HLT theorem in higher dimensions, you can have turning points where the formal decomposition doesn't work. Why doesn't that happen as you move along for a
No, but everything is done in the level of form power series, and there's no actual complex numbers in the.
Oh, so it's formal in the
In everything, yeah, formal in all directions.
When you write, you say deform a bit QMT, can it happen that if you deform too much, like some of the physical values go off?
Yes, yes, no, you can deform as far as your thing makes sense. For example, you can deform over this logic of ring, it will be series and extension, so it will always do. But over complex numbers, it's you just up to convergence radius you can do. So it's, yeah, in fact, here there's actually interesting example here. Here Q is small number, but because it's of positivity here, Q could be take arbitrary values, could go to plus infinity, and if it goes to plus infinity, then it will be something different. If it goes to plus infinity, then you get kind of again regular polygon of regular polygons, but of different size, so will nothing inside. And the reason is in this limit, you write your tree not as a blob, but as a blob in this case is actually bundled with fiber projective space m-1 over another projective space pa+1.
We're talking about this example.
Yes.
Yes, yes, yes.
Yes, yes.
Yeah. Or PA. Yeah, yeah. You take you make it a bundle, and for projective bundles there is another thing. This should be another result. When the projective bundle, you should have copies of your homology of the base repeated many times. So this transition, if Q goes from 0 to infinity, these things kind of move another and arrange different collection of regular polygons. So it's just a long answer.
Any other questions?